So, actually getting to our lesson on the second part of stoichiometry. Today, we are looking at specifically the mole ratio. So, we're still dealing with standard 3C, where we're trying to apply concepts of mole and Avogadro's number to calculate between any of the relationships in a substance. But today, we're focusing on just the mole ratio and those balanced equations. So just remember that your chemical equation provides you a lot of information about the particular reaction. Um, think of it as a recipe. It tells you what and how many of each thing goes into making your particular um, substance. So let's say, random example, I know I want to make 10 turkey sandwiches, and I am trying to determine how many pieces of turkey I need to buy. Well, my equation here tells me that for one sandwich, I need 3 pieces of turkey. So I know that I need to buy a total of 30 pieces of turkey to make my sandwich. Conversely, I could start with the cheese and go to pieces of turkey, and it would still kind of work the same way. Let's say I had 50 pieces of cheese, and I want to know how many pieces of turkey I need to buy to use up all of the cheese. So with 50 pieces of cheese, I know that each sandwich for Miss Raines, because she really, really loves cheese, has 2 pieces of cheese for every 3 pieces of turkey. And early on a Wednesday morning, I cannot do mental math. So 50 times 3 divided it divided by 2 should give me 75, but I don't trust my mental math. Hey, yay, it does give me 75. Um, I need to buy 75 pieces of turkey. So we're not making turkey sandwiches in chemistry. We're actually doing experiments where we're dealing with chemical substances. So this is kind of a simplified example or an idea of what I refer to as the mole ratio. So my coefficients tell me the number of moles of each substance that is used in a chemical reaction. It lets me know how many of each thing goes into making or producing that final product. Now, in order to create your mole ratio, you got to have a balanced chemical equation. So, if you don't have a balanced chemical equation, you're going to have to balance it. Now, mole ratios can be used to convert between any two substances. So, it could be between reactants and products, products and reactants. It could be between any two products or any two reactants. It really doesn't matter as long as it's in that equation and the equation has been balanced. We've got to have that balanced equation. So remember, a couple of units ago, we learned how to balance equations. If you're still struggling with balancing, definitely hop into the Google Meets and get some help from me sooner rather than later. For right now, some of the practice, I'm giving you the balanced equations. Others, you're going to need to balance them yourself. So we still need to keep that skill kind of fresh. Now, this equation, the mole A and mole B. So A and B are arbitrary. A is whatever in the heck the problem is starting with. B is whatever in the heck it's ending up with. So it's just kind of a placeholder. It's if A and B trips you up, then start and end, whatever makes more sense to you. But this is the thing that's on your cheat sheet. And those blanks are there on purpose to remember, to remind you to look at the blanks in the chemical equation. So our conversions, like I said, you have to have that balanced equation, but it's the same basic setup. You're going to write your given number and given units, and then you're going to set up your dimensional analysis by multiplying by a fraction. So whatever unit you're getting rid of, goes on bottom, the unit that you're going to goes on top, and these numbers come from your coefficients, especially for that mole ratio. Try and get in the habit of including your chemical formulas. So, looking at this first example, I'm not giving you the chemical equation at right away, but it's talking about decomposition. So that means my ammonia is breaking down. And we know that if we're looking at decomposition, we're going to assume that it's going to break into the elements. But I got to remember that nitrogen and hydrogen are two of the 7 diatomics. So these are the pieces to my reaction. This is my skeleton equation. But if I notice my number of atoms aren't balanced, so I would have to actually go through and add the coefficients to get everything to balance. So once I balance my coefficients, I end up with my coefficient with my balanced equations, and I can actually do the problem. I can do the calculation that it's asking for. So to give me a little bit more space, I'm going to leave my balanced equation here in red. So it says each product. So I'm actually answering 2 problems at one time. If I start with 6.50 moles of ammonia, how many moles of nitrogen will I produce? That's one of my products. So I know that I'm going from moles of ammonia to moles of nitrogen. I'm getting rid of ammonia and I'm going to nitrogen. So moles of ammonia have to go on bottom, moles of nitrogen go on top, and my coefficients tell me that I end up with a 1 over a 2. So I get 3.25 moles of N2 as my answer for my first product. Looking at the second product, same basic setup. Write your number that is given to you in the problem, multiply by a fraction. So this is a mole to mole. The substance I'm getting rid of goes on bottom. The substance I'm going to goes on top. So I'm getting rid of moles of ammonia. I'm going to moles of hydrogen. My coefficients tell me that this time I'm going to end up with a 2 on bottom and a 3 on top. And I get 9.75 as my answer. Sorry, me and my stylists are not getting along. 2. So if I really, really wanted to show the units and the substances canceling, I can. I typically don't because it kind of starts getting a little messy the further along you go, but we can see that we, stylist, we started with the moles, but it canceled out. I started with NH3, it canceled out. I am left with moles of N2, which is what I wanted. My second one, I can see moles cancels, NH3 cancels, and we're left with moles of hydrogen. So that's your mole ratio. It's, I'd say, about as easy, well, maybe a little bit easier than what we saw the other day with the moles and mass conversion, simply because you're not having to do an extra calculation for molar mass. But it does require you to have that balanced equation. And that's the problem I just did, a little bit cleaner and a little bit nicer. Notice that I am still writing my chemical formulas each time. I'm writing my units each time. As we get further into stoichiometry, this will help make sure you're getting rid of the right substance and the right unit each step of the way. Yes, I know it's tedious, but it will save your sanity a little bit later. So let's look at another example. This one, I'm giving you the balanced chemical equation, and I'm not even giving you words, so it kind of makes it a little bit easier. So I can see my coefficients are 3, 2, 2, and that invisible 1. So if you want to fill in the 1 to remind you that it's there, you're more than welcome to. So my problem is asking me that if I start with 72.5 moles of sodium sulfide, Wow, really bad. How many moles of sodium phosphide would I produce? Bad grammar, bad misreads. Haven't caught that yet, but not gonna go back and fix it right now. So, starting out, I write the number from the problem, my given number, my given unit, and my formula. Oops. 72.5 moles of Na2S. I'm getting rid of moles of Na2S, and I am going to moles of Na3P. So notice both of my substances are starting with sodium. So I got to be very, very mindful of where I'm looking at to get my numbers. So Na sodium phosphide, Na3P is on top, so 2 goes on top. Sodium sulfide, that 3 would go on bottom. And handy dandy calculator on a Wednesday morning gives me 48.33333 until affinity. So I don't want to write a whole bunch of threes. I know that I want to round according to the number of digits that I started with. I started with 4 significant figures, so I'm going to keep 48.33 moles of sodium phosphide. Ooh, typed version. So, next example. Different starting substance, different ending substance. That means my equation, my fraction in the center is going to be different, but it still comes from those coefficients. So aluminum sulfide is what I'm getting rid of. Why is it not? There we go. So aluminum sulfide is what I'm getting rid of. That means that 1 on bottom came from that 1 in that coefficient. Aluminum phosphide is what I'm going to. It's what it's asking about. So that's where this 2 came from on top. It came from the coefficient for aluminum phosphide. Type into my calculator, use the fraction button, whatever makes the most sense to you. And my calculator is only going to tell me 28.9. I got to know, I got to add that extra 0 for my significant figures. If you did watch the opener video, notice, I hope you caught that even though I'm talking about significant figures with each problem, I probably won't be looking at it for most any of the problems. In a typical year, it's 1 point on one question for quizzes and tests. But since I know many of you are going to go take physics next year as juniors and seniors, I'm still stressing it because you're going to see significant figures again. And that was it for today with the mole ratio. So a little bit simpler than what we saw the other day, mainly because you're only looking at one equality statement. You're looking at using mole of whatever I start with and mole of whatever I end up with. And it can be any 2 substances in the problem. I can go from sodium phosphide to aluminum sulfate. I can go from aluminum sulfate to sodium sulfide. It doesn't matter. Hope you guys found this useful. Definitely pop into the Google Meets if you've got any questions or concerns. See ya.